When you look at the data table, over here on the first column, there are these links to the corresponding videos for each row. When you click on this, the video is downloaded. Once you download the video, you are ready to run the tracker. This is the first video. You see the cart, the rope, the pulley, and the hanging mess are here. You can run the video. If you run the video, you see the cart will move after it's released. We have to do some operations on this video first. Come over to this video settings button. On the video settings, the frame rate is put as 50. You have to change it to 52. Taking the data of the cart, our aim is just take the X versus time data for this cart. You are not going to start from the first frame. If you run the tracker frame by frame, you see now we are at the 9th frame and there is no motion at all. If we enlarge this part of the video, you see this finger. When he releases his finger, the motion will start. So, I'm just trying to catch the frame that the finger is just released. So, 13 is going to be my start frame. Why? Because finger has just released the card at this frame. So again, I will come to the video settings. There appears the start frame. Change the start frame to 13. This is going to be different for the rest of all different videos. And next, what about the end frame? End frame is going to be the frame that this hanging mess hit the ground. Well, you will see that it will hit the ground when the rope is just loose. When you see the rope is loose, that means that the hanging mess hit the ground. Just try to catch the last frame on which the rope is still taut. I think this is the frame. So this is the last frame that you will take the data values. So you will only take the data values between this frame and this frame, between 13 and 76. We have to do it because between these frames, the card is doing a constant accelerated motion. So once you set up this, you are ready to take the data values. Come over again, starting frame, which is 13. And next thing is that you have to put your coordinate system. For this, you just press this button And you can put this coordinate system for this experiment anywhere you want. It is not important. But anyway, I will put this origin to the place where you see this white label on the card. I will locate the origin to the bottom corner of this rectangular white label on the card somewhere over here. Because I will start taking the data values or tracking this card, this white label. So once you set the coordinate system, you can just remove it by pressing again on this button. The next thing is that we have to let the tracker know about the scale. On the rail, you see these two square white labels. And between these two square white labels, the distance is 70 centimeters. So we just set it up that this distance is going to be 70 centimeters. And we have to let the tracker know this. For this, just come over this button, New, choose calibration stick. Once you choose the calibration stick, come over the first square white label, press Shift button and hold it. I'm doing this. Observe the mouse pointer. Now, mouse pointers turn out to be a square pointer. Come right center of the white label and press the left mouse button. This is my first mark. And come over to the second label. Over here, do the same. There appears this blue line between two marks, and let this distance to be 0.7 meters. By doing this, I just put my scale on the video. So again, you can remove this by pressing this button again. And everything is ready, except we have to create our object because we are going to produce some data table over here, position versus time. From this data, tracker will be able to determine the acceleration of this card. So come over the Create button and just choose the point mass. Once you choose, the tracker will create the object, naming with mass A. I will rename it M2 because in our setup it is named as M2. Now we are ready to auto-track this card. During this motion in every frame, the tracker will run the video frame by frame, but in every frame, it will take the position and the timing of this card. It will record on the table, and it will also at the same time produce X versus time data. So for this, I will choose a specific point, which is the bottom right corner. This is the part that the tracker will take its position measurements. And for this, I'm pressing the Shift button together with the Control button. Now I'm holding both the Shift and the Control button, and you see there appears a circle sign. Now the mouse pointer turned out to be a circle. Just bring it over this corner that I take as the reference point for taking X measurements for the card and press the left mouse button. Once I pressed it, the tracker produced this red circle being the center on the bottom right corner of this label. That means the tracker will just search for the same shape in each frame, and it will just mark this bottom corner as the position points of this card. It will do this for each frame. Now, the rest is just easy. There appears Auto Tracker window, and all you have to do is just press the search button. As soon as I press search button, the tracker will run the video frame by frame, and on each frame, it will mark the position according to this coordinate system. It will record this position and also its timing on this plot and also on the table. So I'm ready to push the search. You see these data are produced by frame, and also it's drawing all these data on the X versus time graph. So the last frame also done. For all frames that I choose, the tracker just recorded the position and also timing value for the cards in each frame. And it just produced this X versus time graph. X being the horizontal direction for the video. You see, it's a kind of parabola. It's very clear from this picture, even we haven't started analyzing yet, it's a parabola. And the parabola is nothing but the position versus time plot for the kind of motion which has constant acceleration. We don't need this window anymore. Just remove it. So what next? Remember, our job is calculate the acceleration for that specific video. You can do this both ways. We can do this either analyzing X versus time graph and curve fitting this and finding the parameters AT squared plus BT plus C, and A is going to be just half of the acceleration. But also, you can convert this velocity versus time graph. So you see, I just pressed on the label for the vertical axis. I can choose any physical quantity over here. if you choose Vx, the velocity of the kart in the x direction, the tracker will convert the position time data to velocity versus time data. And you see the velocity versus time plot appears to be a straight line. And this is what you expect for a constant accelerated motion, because the velocity will increase linearly for a constant accelerated motion. Might suggest that to calculate acceleration, use v versus time plot. And on this plot, press right mouse button and choose Analyze. And there will appear this Analyze Data tool window. You again see the v versus time plot, also together with the v and t data values over here. So we will analyze this plot by drawing a straight line curve it and choose this one. And now the tracker automatically draws baseline that fits this data, and it calculated what the acceleration is. And the equation that fits to the data, Vx is equal to a times t plus b. V is equal to at plus b is an equation for the velocity for a constant accelerated motion. And in front of t, this parameter a is going to be your acceleration. So it's calculated to be 8.621 times 10 to the minus 1 meters per second squared. Let me write it over here. We know that this is the plot for V is equal to a times t. There is also a V0 parameter over here, but since this parameter is very small, 10 to the minus 3, that means the initial velocity of the kart is almost 0. So you don't need this. So our equation for the data set that V data, which are these columns, and T data, which is the first column here, is connected by acceleration. And if you find the uncertainty in the acceleration, you have to use this equation. Delta A is A multiplied by in the square root delta V divided by V squared plus delta T divided by T squared. This is the formula to calculate delta A. And A, as I said, is just this A parameter. What about this? This delta V, for example. When you come over here, this window, that you get the best fit and the parameters, etc., you also See this root mean square deviation. This root mean squared deviation for this graph of the variable the vertical axis, Vx. So, this is the error or uncertainty on the vertical axis, which is V. So that means this is delta V. And I just read over here this value, which is root mean square on this plot. I'm reading 5.846 times 10 to the minus 3. Of course, delta V is meter per second. This value you put over here in this equation. What about V? V is the last velocity value, the velocity value of the cart on the last frame. We are on this graph. If you push your button over here, the last data, there appears this yellow label over here. On this yellow label, you will see the second number. Vx is the last velocity, which is, I read, 1.022. This is 1.022 meters per second. And what about the next parenthesis? The next one, delta t divided by t. So, how do you get delta t? The root mean squared deviation on over here is just the uncertainty of the variable which shows the vertical axis on this graph. If I change this vertical axis somehow to t and put this t-axis over here, the vertical, and v-axis to be horizontal, the root mean squared deviation value will be the uncertainty in time measurements. You can do on tracker. If you just come over Vx, there appears this t over here. If you select t, t is being the vertical axis and v being the horizontal axis. But you have to also check this autofit checkbox so that the tracker fits this data to the baseline. So when you do this, all these data is plotted in a different way. Only difference is that t values are on the vertical and v values are on the horizontal axis. The tracker again calculate the root mean squared of this t-axis. So you see this root mean square value has changed with respect to the previous one, where v was here. But now t is here and the root mean squared value is different because this is the root mean square for t. This is delta t. So delta t is calculated 6.780 times 10 to the minus 3 seconds. you put it over here. And t is the timing of the last data point. Which is I rate to be 1.195 seconds. For this equation, for the uncertainty in A, this is how you calculate. A is calculated slope value for the V versus time graph. Delta V is root mean squared in V. V is the velocity value for the last frame. Delta T is root mean squared for T, and T is the timing for the last frame. And you just plug and chuck all these values and calculate what the delta A. And put this over here, the first row, next to it. So this is how you calculate A and delta A. Of course, you have to also calculate and put the values for T, delta T, Fnet, and delta Fnet. And what is T? T is the force that moves the cart. That moves M2 because this is the tension in the cord. It's the only force that pulls M2 towards right, so that M2 moves as an accelerated motion. So what do you know about this T? Of course, it should be equal to just the mass of the object multiplied by its acceleration. Acceleration is already calculated from the tracker, so you can put over here acceleration. And you know what the M2 value? M2 value is this one. You put this value over here, then that's it. You just calculated T and put this value over here. And next, what about delta T? For delta T, use this formula. Delta M2 is over here, the uncertainty in mass measurement. It's just 0.5 grams. M2 is just 525.9 grams. Delta A is calculated from here, and A is already calculated by the tracker. Put these values over here, and that's it. This is going to be delta T. So what about Fnet? Fnet is the weight for the hanging mass, because the gravity on this hanging mass is the force that moves all the system. And we know that Fnet is just equal to sum of masses m1 plus m2, both hanging mass plus the cart mass, multiplied by A. So, you just calculate this from the calculated value of A over here, put this value over here, and you know what the masses are from Here, M1 is just 50.3 grams and M2 is 525.9 grams. Put them over here and calculate Fnet and put it over here on this cell. And delta F, I just leave it to you. You can utilize these formulas. So this is the way of filling out the first row for this table, and all the rest you are going to do yourself by using the corresponding videos for each row. You download it and put it on the tracker and work it out by the way that I showed you. What next is after filling out this table? What next is that you will plot t versus a graph. And for t values, these column values are going to be your data values. Put all these t values over here. And a values are also going to be your data values. Put all these a values over here on this x-axis, the horizontal axis. And suppose that the first t value and a value produce this data point somewhere over here, and the next one somewhere over here, the other one is over here, the other one is over here, and next one somewhere over here. And you will see that after putting all these data, again by using tracker, you will make a curve fit and it will draw a straight line. And it will just calculate the slope of this by calculating a parameter. And the slope of this is going to be just M2 value, but it's going to be experimental value of M2. This M2 values is just measured values. These are measured values by our electronic scale. And this value is going to be the experimental value by using the Newton's second law. And you will just make a comparison that how these values are close to each other. And you have to also find the experimental error on this. And you will do this by using the techniques that I showed you already. So then you will be completing the first part of your report. In the second part, there are videos again. This time, M1 mass remain the same for each video, while the M2 mass increases for each row. This time, we expect the acceleration to decrease in each row. In this part, after calculating A and delta A, calculate the last column. This time, you will plot M2 versus G minus A over A graph, and the slope of this graph is equal to experimental M1 value. Again, compare it to the measured value of M1 and find the experimental error on this. So then you will be completing your report and it is going to be of your third lab.